Hello and welcome guys. Now in this video we will be learning about very important aspect of gradient descent. So that is what all challenges gradient descent basically faces. Okay. So in machine learning these terms are often used as a context of optimization algorithm, and the very first challenge is point of convergence. Okay. So let's say you have a normal distribution of data like this. Okay. I'm very bad at drawing. Okay. So let's say this is your normal distribution. Okay. Now there is a point. Okay, there is a point. So suppose this is a point. Okay, your current error is here. Now if you just imagine moving from here, moving, I mean, let's say you are reducing the error from here. Okay, now your step size will be like this. Okay, step size will be like this. At certain point you will see that from here to here, the error reduction was very negligible. I mean, it was very less that you can't even count it. Okay, at that time the point of convergence basically occurs. So basically gradient descent won't be able to calculate the reduction in error. It was very small that it won't be able, it won't matter actually. Okay, and that is what point of convergence is. So you can see, right, I mean, the improvement can further happen, but because of the way gradient descent has been built, at certain point, after reaching a certain point, this point of convergence will happen and it will say that we have converged and there is no further improvement. So what basically this point of convergence is saying is that so basically the algorithm will stop updating the parameter if it reaches sufficient amount of good solution. So the algorithm may not have found best possible solution that we have seen here, but it has converged to a point where improvement in the objective function is negligible. So it will be like point 0.00001, 0.00002, like that. Okay, so the improvement you can't even count. That type of improvement will be negligible, and that is what point of convergence is. So for example, you are training a neural network to classify images of cat and dog. After several iteration, the optimization algorithm, the performance of the validation set has stopped significantly improving. At this point you can say that algorithm has been converged according to gradient descent. But isn't it actually improve? No, right? Exactly, it is not improved, but gradient descent wouldn't be able to fix that. But there is a different type of gradient descent that will help us reach the global minimum. So we'll see that in the later part of this video. Now let's understand the global minimum, the another challenge. So this referred to the lowest point in the objective function surface, which correspond to best possible solution. So finding the global minimum is often an ultimate goal in optimization, but it can be difficult in high dimensional space. So you can see, right, in one dimensional space you can easily go towards your global minimum because you just have 2D data. But what if your data is 3D, like this? What if your data is like this? You will have multiple peaks, multiple lower points. Okay, and if I show you the animation, it basically looks like this. Okay, let me close this. Yeah, you can see that this particular point has been stopped there because it didn't got that jump in the step size to jump out of this particular uh, saddle point. It's also called as a saddle point. It's basically a point of the function that is neither a local minimum or a maximum. Okay, so it couldn't able to jump the the saddle point, and this is what actually happens when finding global minimum with high dimensional data. Okay, so hope it is clear that if when we have high dimensional data, we can have multiple local minimas as well as one global minima. Okay, so so suppose you are trying to fit a linear regression model with a data set using gradient descent. If the objective function is complex, there will be one global minimum which correspond to best possible fit to the data. Okay, hope that is clear. Now let's understand the concept of local minimum. Okay, so basically this refer to a point in the objective function surface that is lower than all nearby point but not the absolute lowest point. Okay, so like this one, like I told you in the previous example in the so you can see here in the previous slide we have noted that it couldn't able to surpass the saddle point. Okay, so that is what local minima looks like. So this is how basically you can see that that particular local minima it couldn't able to surpass. Okay, because of the saddle point. So these type of challenges gradient descent face. Okay, so example, suppose you are training a neural network with multiple hidden layers. The objective function surface may have so many local minimum that correspond to good solution but not necessarily the best possible solution. So gradient descent can sometime get stuck in the local minimum and fail to find the global minimum, which is in this case is this particular point. Okay, this particular point. Okay, this is the global minimum. Now what is saddle point? Like I just tell you, this refer to a point of the objective surface where the gradient is 0 in one direction but not in other direction. You can see that here the direction will be 0, but if you come from this direction it won't be 0. Okay, so at a saddle point the objective function is relatively flat in some direction but steep in other. You can see the steep is very high in this direction. Okay, so so at the saddle point the objective objective is to you know jump higher and find the global minimum point. Okay, so example, you are training a neural network with many parameters. The objective function surface may have many saddle point which can slow down optimization algorithm that rely on the gradient. So in some cases saddle point can be worse than the local minimum because they can trap the algorithm in the plateau region. Okay, and these are the plateau region. Okay, like I show you, these are the plateau region where your algorithm may get trapped. Okay, so hope this is clear. This is also a like a plateau region, saddle point. So these type of point where these type of simplest gradient descent algorithm may get confused and may not find us the global minimum. Okay, now we'll see how to solve these challenges. Okay, so let's move to the another slide. Let's understand what are the different type of gradient descent we have. Okay, so let's remove all this. Yep. Now before we understand different type of gradient descent, let me tell you what are the disadvantage of local minimum and saddle point. Okay, because that is very important to understand. So you see that saddle points we can find out our saddle point here, and this is the plateau region. Okay, like I just show you, this is like a plateau region and this is saddle point. So local minimum can lead to suboptimal solution where the algorithm converges to local minimum instead of global minimum, resulting in less accurate model. Now saddle point can also slow down or prevent convergence of the optimization algorithm as the gradient is close to 0 but the point is not minimum. Okay, here actually. So what can go wrong in the model while inferencing? First is overfitting, second is underfitting, third is extrapolation. Now overfitting tells when the model is too complex and learn the noise in the training data, resulting in poor generalization to new data. Underfitting says when the model is too simple and cannot able to capture the underlying pattern in the data, resulting in poor performance on both the training and test data. Extrapolation says when the model is used to make prediction outside the range of training data, resulting in unreliable prediction. And last one is input error. So basically when the input data contain error or missing values, that leads to incorrect predictions. Okay, and these are the disadvantage when we were having multiple local minimum as well as saddle point in our data. Now let's understand this one. Now basically we have three different type of gradient descent. First is batch, second is stochastic, third is mini batch. So basically batch gradient descent says the model parameter is updated after computing the gradient over the entire training set. So this approach can computationally expensive, especially for large data set, but it guarantees convergence to a minimum, and that is what basically solves the problem of normal gradient descent. So batch gradient descent is generally used for a small to medium sized data set. Now what stochastic gradient descent says? It says that the model parameter is updated after computing the computing the gradient descent of each training example one by one. So this approach is less computationally expensive than the batch gradient descent, but can be less stable as it can sometimes overshoot the minimum. So stochastic gradient descent is generally used when we have large amount of data. Now the last one is mini batch gradient descent. So what mini batch gradient descent says? It is comprised of basically both batch and stochastic gradient descent. In this approach, the model parameter are updated after computing the gradient for a small randomly selected subset of the training set. So this approach can be more efficient than batch gradient descent and more stable than stochastic gradient descent. So both batch gradient descent and stochastic gradient descent have their own advantages and disadvantages. So batch gradient descent says it guarantee to converge to global minimum if the learning rate is sufficiently small. Like I told you, right? I mean, if we have distribution like this and our step size is small, it will be very easy to reach the minimum point. But if our learning rate is high, then our step size will be like this, and we might miss the global minimum. Okay, so that is what it says, and then it converges smoothly and more stable compared to stochastic gradient descent. It can be parallel across multiple CPU and GPUs to speed up the computations. It allows that as well. Then what are the disadvantages? So it requires the entire data to be loaded into memory, and that is the biggest disadvantage of this method, which can lead to problem if the dataset is large. It can be slower than stochastic gradient descent for large data sets, because the learning rate is small, and the step will be very small as well. So one more problem is it can get stuck in the local minimum if the initial starting point is not chosen correctly. Okay, so imagine your initial point has been chooses this one, then it will won't guarantee that it will reach here. Okay, that is what it says. It need to be correct, the starting point, so it should be this particular starting point, then only it will be able to reach the minimum, local minimum. I mean, by passing all of the local minimum, it can reach the global minimum, and that is what it says. So when chosen wrong starting point, it can lead to wrong you know wrong local minimum, and it won't be able to come towards the global minimum, and that is what the main disadvantage is. But right, when I mean, when to choose what, and that is what it says. So now let's move to stochastic gradient descent. So basically, it is computationally faster and more efficient for large data set, as it updates the parameter after each training example. It can escape the local minimum and saddle point. So in future projects, you will see that most of the point we use stochastic gradient descent, and the main reason is it can escape from local minimum and saddle point. So what is disadvantage? So disadvantage is it can be more unstable and noisy due to frequent updates, and it may not converge to global minimum and may get stuck in the local minimum saddle point. But it may require more iteration to converge to the optimal solution. So I mean, it can get stuck, but it also guarantee that if the iterations are higher, it can reach global minimum in that case also. Now the question is, which type of gradient descent to use depend on obviously the size of data set, the size of amount of computational resource available, and the desired accuracy of the model. So if the data set is small and the computation required is not a concern, then batch gradient descent can be used for accurate results. So if the data set is large, which in most of the cases it will be, stochastic gradient descent or mini batch gradient descent can be used to speed up the training process. If the data set is very large and distributed across multiple machines, distributed gradient descent can be used to improve the scalability. For example, in image recognition, where large data set are commonly used, stochastic and mini batch gradient descent may be used in contrast to financial modeling, where accuracy is critical and the data set is usually small, and batch gradient descent may be a better choice in that case. Okay, so hope it is clear when to use what and what are the advantages disadvantages of all the gradient descent we have. So in future, just remember, most of the time since mini batch gradient descent is combination of both stochastic gradient descent and batch gradient descent, it has some disadvantages also. So most of the case in which while solving a problem, you will see that stochastic gradient descent is decent in all the cases. Okay, so that's all in this video. See you around. Thank you.